Welcome to this explainer. Today, we're diving into the absolute immense scale and, honestly, the incredibly complex mechanics behind how dams are built and how they literally power our world. I mean, when you stand at the base of a modern megadam, you are looking at one of the most audacious feats of human engineering ever conceived. We're talking about millions of tons of concrete holding back literally billions of gallons of water. But, these colossal structures aren't just giant walls. They are highly calibrated, heavy-duty engines designed to capture the raw, completely untamed energy of nature and convert it into the electricity that lights up our homes, charges our phones, and keeps our cities running. So let's unpack exactly how that whole process happens.
Okay, here's our roadmap for today. Number 1, taming the flowing river. 2, building the megastructure. And 3, generating hydroelectric power.
Right, so before we get into the heavy engineering and all the electrical components, we really have to confront what seems like an impossible puzzle. Think about it. Have you ever watched a raging river after a heavy storm? The sheer force is absolutely relentless. It sweeps away boulders, trees, earth, like it's nothing at all. So imagine trying to lay a precise, perfectly leveled concrete foundation right smack in the middle of all that chaos. You can't just pour wet concrete into rushing water and expect it to set, right? It would wash away in seconds. It's this incredible paradox. To harness the river, you first have to defeat it. So let's get into part 1, taming the flowing river.
To solve that crazy engineering puzzle, we have to start at the very beginning, with the river itself. You literally cannot build until you route that raging water completely away from your construction site. So phase 1, diverting the river, takes months of meticulous work. Engineers usually have to blast these enormous bypass tunnels straight through the solid rock of the canyon walls. And just to give you an idea of the true scale here, these tunnels can easily reach 50 feet in diameter. They're massive. Once those bypass tunnels are ready, they build temporary earthen dams, which are called cofferdams, across the river just to force the water into these new man-made routes. Suddenly, the natural riverbed is completely exposed. It's bone dry. And it's only then that we can move into phase 2, pouring the foundation, and phase 3, erecting the wall. And those are processes that take years of continuous, grueling labor.
Which brings us to part 2, building the megastructure. Okay, now that we actually have a dry, diverted riverbed, the sheer scale of the project truly comes into focus. The tonnage of concrete required here is mind-boggling. We're talking about millions upon millions of tons. But here is a fascinating little detail that most people don't realize. Pacing the pour is absolutely critical for a structure of this size. See, concrete doesn't just dry. Actually, scratch that. It cures through a chemical reaction. And that reaction releases an intense amount of heat. Back during the construction of the Hoover Dam, engineers realized that if they just poured the entire dam at once, the heat generated would be so extreme that it would take 125 years just to cool down. The concrete would just crack and shatter in the process, completely ruining the dam. So, to prevent a catastrophic failure, they have to pour the concrete in a series of interlocking blocks. And get this, they embed miles of metal tubing carrying ice-cold water just to cool the structure from the inside out. It's this delicate, years-long balancing act of chemistry and physics. All right, moving right along to part 3, generating hydroelectric power. With the physical structure complete and the water finally filling in behind our giant concrete wall, we reach the climax of the whole thing, turning that immense flow of water into electricity. To make the invisible visible here, we need to learn the internal anatomy of the dam. When you look at the face of a dam from the outside, it just looks like a solid wall. But inside, it is hollowed out with these giant conduits. And the absolute most important of these is the penstock. The penstock is this steeply inclined, heavy-duty tube that channels water from the reservoir all the way at the top, plunging it deep, deep inside the structure. Because it drops at such a steep angle, gravity just takes over completely. The water accelerates, and the pressure builds to extraordinary levels. By the time that water reaches the bottom of the chute, it is essentially a high-pressure water cannon. And here is the crucial point. That high-pressure water hits the turbine next. You can kind of think of the turbine as a heavy-duty propeller. All that water roaring down the penstock is directed right at the precisely angled blades of this gigantic mechanical wheel. The sheer kinetic force of the rushing water slams into those blades, causing the entire turbine assembly to spin incredibly fast. So the water has done its job, right? It transferred its rushing energy into rotational energy, and then it just flows out the bottom of the dam and continues on down the river. But that spinning turbine, that is now the beating heart of our entire operation. Finally, we reach the generator. This is the component that actually translates all that mechanical spinning into the power that lights up a whole city. The turbine is connected by a long metal shaft directly up into the generator. And inside the generator, we're dealing with electromagnetism on a really grand scale. So the spinning shaft turns a giant rotor that's completely covered in electromagnets. These magnets are spinning incredibly fast past a stationary ring of copper wire coils. As the magnetic fields sweep past the copper wire, they literally pull on the electrons inside the copper atoms, forcing them to move. And this movement of electrons at the subatomic level, that is exactly what an electrical current is. Just like that, we have created electricity. You know, looking back at it, this entire process is just a masterclass in physics. It perfectly tracks the physical conversion of energy step by step right through the dam's anatomy. Step 1, the water sitting high up in the reservoir holds potential energy. It has the potential to fall. Step 2, as it rushes down that penstock, that potential transforms into kinetic energy, the energy of motion. Step 3, when that moving water strikes the turbine, it becomes mechanical energy as that giant wheel physically spins. And finally, step 4, the generator converts that mechanical spin into electrical energy. It's just this beautiful, uninterrupted chain reaction of physics perfectly engineered to capture nature's power.
So as we wrap up this explainer, I want to leave you with a final, kind of provocative thought. We know these dams are marvels of engineering, right? They provide immense amounts of clean energy by mastering some seriously complex fluid mechanics and electromagnetism. But as our world demands more and more power, how exactly will these megastructures fit into our evolving energy grid? Are we going to continue to build them bigger and bigger? Or will we find new ways to refine these incredible mechanical processes? The complex engineering we explored today is really just the beginning of that conversation. Anyway, thank you so much for joining me for this explainer, and keep questioning how the world around you works.